in previous lectures we investigated a structure what is called a parallel plane waveguide. So, if you are having two conducting boundaries, we saw that the electromagnetic energy can propagate between these two boundaries in the form of some definite electric and magnetic field patterns which we call as modes. We also try to visualize the propagation of electromagnetic wave between these two boundaries as a superposition of uniform plane waves. Now, this understanding of modal propagation in terms of the uniform plane wave gives you a correct picture of how the modes actually are established inside a waveguide. However, this approach that visualizing a modal pattern in terms of the fields of uniform plane wave is always not that easy as we saw in terms of parallel plane waveguide. In parallel plane waveguide, since the medium still was infinite, at least parallel to the conducting boundaries, we still could use or visualize the uniform plane waves propagating between the boundaries. However, if I have a structure, let us say like a pipe kind of structure, whether it is a rectangular pipe or circular pipe or a pipe of arbitrary shape, and if I want to find out how the electromagnetic energy is going to propagate inside this structure, it will be extremely difficult to visualize the propagation in terms of superposition of uniform plane waves. And in those situations, essentially we go more mathematically. So, we develop a mathematical framework and try to solve the problem of electromagnetic wave propagation in a structure using the general mathematical formulation. So, in this lecture essentially we develop now a general framework for analyzing wave propagation inside a arbitrary waveguide, and then we will, whatever results we get now mathematically, we will try to correlate these results with what we have got for parallel plane waveguide, which we visualize as a superposition of uniform plane waves. So, that will give us confidence that the visualization which we had in terms of uniform plane waves was indeed correct, and that gives you a much better physical insight into the problem. However, since every time resolving into uniform plane wave will not be possible, now we will develop a general mathematical framework and solve the problems in the following by using this general mathematical approach. So, in this lecture essentially we do the analysis of a waveguide, what is called a general approach. So, idea now here is as follows. Let us say if I have some arbitrary shape waveguide, this is a pipe which I call waveguide. So, this is a conducting pipe, and the electromagnetic energy can flow along the axis of this pipe. So, there is a wave propagation in this direction. So, that is where the wave is going to propagate, and at the moment I am not even defining any shape for the cross section. It could be rectangular, it could be circular, or in general it could be as arbitrarily shaped as shown here. So, only information I want to use now for this analysis is that the wave is going to propagate in this direction, which is the axis, and then without losing generality I can say this direction is the z direction. So, I can orient my coordinate system such that I may have this direction x, this is y, and this is z. This is z, this is x, and this is y. So, xy plane is the like a cross sectional plane for this waveguide, and the wave is going to propagate in the z direction, which is the axis of this pipe, what is called waveguide. So, now we develop a general framework starting from the Maxwell's equations. What kind of fields would exist inside this, and then we will later on we will deal with very specific cases, rectangular waveguides and propagation of modal propagation inside a rectangular waveguide. Now, since this direction is a special direction, I call this direction as the longitudinal direction, because this is the direction in which the wave is going to propagate, and a direction perpendicular to this direction we call as the transverse direction. So, we say this direction is longitudinal. So, any field component which is in this direction we call as the longitudinal field. Any field which is perpendicular to this wave propagation, that we will call as the transverse field. Any electric or magnetic field, now we will resolve into two components. One is along the wave propagation, that will be, we will call a longitudinal component, and other one will be perpendicular to direction of wave propagation, that we will call as a transverse component. Since the longitudinal direction is the same direction as z, essentially we will say that any field now has two components, one is transverse component and other one is the z component. If we do that, then I can now write down the electric and magnetic field in general. So, I have here electric field which is a vector. This can be represented by electric transverse field which is a vector, because it can lie anywhere in the xy plane, plus it has a longitudinal component, and let us say its value is Ez and it is oriented in z direction. So, Ez is a scalar quantity and E transverse is a vector quantity, and this vector lies in the xy plane which is the transverse plane. Similarly, I can write down the magnetic field also, that is the transverse magnetic field plus the longitudinal component of the magnetic field with a unit vector in the z direction. So, any electric field or magnetic field can be represented by a combination of a longitudinal component, this quantity is scalar, and a transverse component which is this, which is a vector. So, by definition then we will have E perpendicular, this vector will be the x component of electric field with unit vector x plus y component of electric field with unit vector y, and same is true for the transverse magnetic field, which will be having x component with unit vector x plus y component with unit vector y. Now, as we have defined the longitudinal and transverse fields, we can also define the del operator and separate it out for longitudinal and transverse component. So, we can define this operator del also as del transverse plus the longitudinal part of that, which is d by dz with unit vector z. So, this is the vector operator, this is the scalar operator d by dz with unit vector z, and this quantity is del perpendicular is nothing but d by dx x plus d by dy into y. So, we define now the fields with their explicit transverse and longitudinal components. We also define the vector operator del in terms of its transverse and longitudinal component. Now, we can just take this and substitute into your any of the Maxwell's equations, and we can take the Maxwell's equation del cross E, that is equal to minus j omega mu into h. So, I can substitute now for E, which is E transverse E longitudinal, H is H transverse H longitudinal, and del, which is given by this. So, I get this equation written explicitly for transverse and longitudinal components, that will be now del transverse plus d by dz z cross the electric field, which is E transverse plus E z z, that is equal to minus j omega mu into H transverse plus H z z. I can open these brackets. From here I will get, so this gives me del transverse cross E transverse plus del transverse cross E z z plus this term d by dz z cross E transverse plus this term, which is d by dz z cross E z z, that is equal to minus j omega mu into H transverse plus H longitudinal with unit vector z. Now, we can note the following things, that if I take the cross product with z, so if I take any cross product with z, that cross product will always lie in the transverse plane. So, if I take this quantity here, the del cross with the z cross z unit vector, this quantity will be a transverse component, this will be a transverse component, but this quantity if I look at, then this quantity will lie along the z direction, because this vector del vector is in transverse plane, this E transverse is in the transverse plane, which is xy plane. So, the cross product of these two must lie perpendicular to that plane. So, this component essentially is the longitudinal component, and similarly this quantity here, which is z cross z, this quantity is identically 0. So, what I now find is that this term is longitudinal, this is transverse because it is cross with z, this is transverse cross with z, and this quantity is identically 0. So, what we can do is we can now separate out the longitudinal and transverse components and equate them on two sides. So, if I take a transverse component, which is this and this, that should be equal to the transverse component on the right hand side. So, from here I get minus j omega mu H transverse, that will be equal to this quantity, which is del transverse cross E z z plus d by dz z cross E transverse. I can bring this minus j omega mu down here to get explicitly this quantity which is S transverse. So, this you give me S transverse, that will be minus 1 upon j omega mu into this thing which is del transverse cross E z z plus d by dz z cross E transverse. Similarly, if I take the other equation for the curl equation, instead of taking del cross E, if I take the other equation and again assume that the medium which is filling this waveguide is ideal dielectric, there is no conductivity, that means there is no conduction current. I can start with this equation that del cross H, that is equal to j omega epsilon into E. Again I substitute for E with the transverse component and longitudinal component, and same for the operator for the del. I will get on the lines similar to this, I will get the transverse component of the electric field, and that will be E transverse, that will be equal to 1 upon j omega epsilon del transverse cross Sz z plus d by dz z cross H transverse. So, see here this expression is identical to this. This is the expression which we had for H transverse. So, minus j omega mu is replaced by j omega epsilon, and Ez is replaced by Z, and E transverse is replaced by H transverse. So, now we got these two equations where the H transverse and E transverse are related. Similarly, here the H transverse and E transverse are related. Now, we can substitute H transverse from this equation into this equation, and if I do that and then bring the E transverse term on one side, so substituting for H transverse from here into this and bringing the terms on one side, essentially we get expression which will be omega square mu epsilon E transverse minus d by dz z cross d by dz z cross E transverse and that will be equal to minus j omega mu del transverse cross Hz z plus d by dz z cross del transverse cross Ez z. So, just we have taken this transverse component here and substituted into this to get expression like that. Now, what we do, we use the vector identity, and that is if I have 3 vectors, vector triple product. So, we can use identity for vector triple product that is, if I have 3 vectors A, B, C, then the triple product A cross B cross C is equal to A dot C B minus A dot B C. So, using this vector identity, then I can look at each of this product here. So, I have a triple vector product here and I have a triple vector product here. So, I can expand these by using this identity. So, let us look at the terms one by one. So, first let us look at the term which is this term. If I write down this term here, that is d by dz z cross d by dz z cross E transverse, and I substitute now use this vector identity. So, I get A dot C B minus A dot B C, which is this vector. So, this we can write as d by dz of d by dz z dot E transverse z minus d by dz z dot d by dz z to E transverse. Now, this quantity, this is the vector which is in z direction. The E transverse vector is in the transverse plane. So, it is perpendicular to z direction. So, this dot product is identically 0. So, this product, the first product here, this quantity essentially is nothing but minus d2 by dz square E perpendicular or E transverse. This is one simplification we got for this term. Same thing we can do for this term also, is a triple product again. So, this term which is d by dz z cross del transverse cross Ez z that is equal to del transverse d by dz z dot Ez z minus d by dz z dot del transverse Ez z. Now, this is again, this del transverse is a vector which is in the transverse plane, that means dot product of z and this will be again identically 0. So, as we have said, this quantity was 0, same is here, this quantity is identically 0. So, what we get from here this triple product, that will be equal to del transverse, and this is the dot product of z and z. So, this will be simply d by dz of Ez. So, this quantity is d Ez by dz. Once we get now this simplification, I can substitute now for this quantity here, which is minus d2 by dz square E transverse for this term, and for this term I have got this quantity. So, this equation which we had for the transverse component of electric field now can be written as omega square mu epsilon plus d2 by dz square E transverse is E transverse here that is equal to minus j omega mu del transverse cross Hz z plus del transverse d Ez by dz. Up till now we have just taken two Maxwell's equations and just applied some vector identities and derived now the expressions which are for the transverse component of the electric field in terms of essentially the longitudinal components. And why we did that is that since the waveguide is a structure in which the wave is going to propagate in z direction, this is the spatial direction, that is the direction in which ultimately the energy is going to flow. We also know that since the 6 components of the electric and magnetic fields are related through Maxwell's equations, all the 6 components are not independent components. So, we can choose 2 of the components as independent components and can represent the remaining 4 components in terms of these 2 components by using the Maxwell's equations. Now, since this direction is the spatial direction in which the wave is propagating, generally we take the electric and magnetic field components which are in this direction, that is the longitudinal component, as independent components and try to express the transverse fields in terms of the longitudinal components. And precisely that is what we did. We now got the expression for the transverse field in terms of the longitudinal component, which is Ez and Sz. So, we treat Ez and Sz are the independent components. So, solve essentially finally the problem for Ez and Sz. Once we get Ez and Sz, then we can find out the transverse field components by using this relation. Now, since our problem again is the wave propagation in the z direction, we are assuming essentially the wave is travelling in the z direction. That means the travelling wave behavior, as we have seen earlier, can be given as e to the power minus gamma z, where gamma is the propagation constant in the z direction. So, the wave travels in the z direction with a propagation constant gamma. So, since we are now interested in the travelling wave inside the structure, we assume that functional form of any field, electric or magnetic, in the z direction will be given as e to the power minus gamma z. Once we get that, then we know for a travelling wave in z direction, the E and H, they will be having varying at e to the power minus gamma z, where gamma is the propagation constant, and then all the derivatives which we have with respect to z can be equivalent to multiplying that quantity by minus gamma. So, from here we get d by dz is multiplying the quantity by minus gamma, and d2 by dz square, that is equal to gamma square. So, this quantity gamma we have not found out what, but we know this is the one which is going to control the behavior of the wave propagation on this structure. So, we know this is called the propagation constant. So, I can replace now d by dz by minus gamma and d2 by dz square in this expression by gamma square. Once I do that, then I can get now the expression which will be omega square mu epsilon plus gamma square E transverse, that is equal to minus j omega mu del transverse cross h z z plus this quantity, and d by dz is multiplying by minus gamma. So, that is minus gamma del perpendicular Ez. Now, for the brevity reason, let us define this quantity which is omega square mu epsilon plus gamma square as something h square. So, let us define omega square mu epsilon plus gamma square is equal to some quantity h square. We will assign some physical meaning later what this h would represent, but at the moment just algebraically define this whole term as h square. Once we do that, then I can now have a final expression for the transverse electric field that will be equal to minus j omega mu upon s square del perpendicular cross h z z minus gamma upon h square del transverse Ez. And on the similar lines, if I use other equation for the transverse component of magnetic field, I would get the identical expression for the transverse component of magnetic field, where minus j omega mu is replaced by j omega epsilon, and Ez and Hz are interchanged. We get j omega epsilon divided by h square del transverse cross Ez z minus gamma upon h square del transverse hz. What is this quantity representing? This quantity is representing a curl in the transverse plane, whereas this quantity is representing the gradient of this quantity Ez, which is a scalar quantity in the transverse plane. So, essentially now if we can solve the problem of wave propagation in terms of Ez and Hz, then we can find out the corresponding fields that in the transverse plane, which are E transverse and H transverse. So now the approach for solving the problem in general will be as follows. We take a geometry in which we want to study the wave propagation, find the solution for Ez and Hz for the geometry, then substitute into these expressions, and then you get the component of transverse fields, that is Ex, Ey, Hx and Hy. Now looking at this expression, we can make certain conclusions. Firstly, if we assume that this medium is completely lossless, then this quantity gamma, which is the propagation constant, is purely imaginary, because the wave is travelling and its amplitude is not going to change. So for a lossless medium, we know that gamma should be J beta. So if I consider a medium which is lossless medium, that means the conducting boundaries are ideal. The medium which is filling this pipe or this waveguide is also a ideal dielectric. So for this we have gamma which is equal to J beta. So your H which we have defined here, this quantity is minus beta square. So you have you get omega square mu epsilon minus beta square is equal to H square. Now this is the beta is the propagation constant in the z direction, or let me put beta bar as we have taken earlier for a parallel plane waveguide. So this is now the phase constant in the z direction. If you recall, this quantity omega square root mu epsilon was the phase constant of the wave in that unbound medium. So then you find this quantity H is nothing but the propagation constant of this wave in the transverse plane. So H represents the propagation constant of a wave in the transverse plane, that means in the xy plane. Now from this expression, now few conclusions can be drawn. Firstly, if the transverse fields have to exist, then both Ez and Hz need not be 0 or need not be non-zero. Even if any one of them is non-zero, still I can get the transverse fields. That means I can have the field distribution inside this waveguide with either Ez equal to 0 or Hz equal to 0 or both of them non-zero. However, if both of them are 0, then the transverse field do not exist in general except when H is equal to 0. So now we have some interesting conclusions can be drawn from this result. That is, for fields to survive inside the structure, both Ez and Hz cannot be 0 except in the case when H is equal to 0. So we see from here a conclusion. One, both Ez and Hz cannot be 0 except when H is equal to 0. Not only that, when H is equal to 0, to have the finite fields, transverse fields, the Ez and Hz must be identically 0. So even converse is that when H is equal to 0, Ez and Hz must be 0. So let us say first, if a H is not equal to 0, then any of the quantities non-zero will still give me the fields. So, these fields will survive. So, now if I take Ez equal to 0, I will get the fields which will be Hz and the transverse field which will be electric and magnetic fields. But for this situation, the electric, since Ez is 0, the electric field is completely transverse, because there is only component of electric field which is E transverse, and this field configuration then we can designate as a transverse electric configuration, as we have done in the parallel plane waveguide. So, now from the general analysis we say when Ez equal to 0 and Hz is not equal to 0, we get a configuration for the fields which will be nothing but the transverse electric configuration. Similarly, when Ez is not equal to 0, but Hz is 0, that gives me now the magnetic fields for which the fields lie only in the transverse direction. So, that we get field configuration which is nothing but the transverse magnetic configuration. The third configuration, which is when Ez is equal to 0 and Hz is equal to 0, this will give me the field transverse fields provided when H is equal to 0. But when Ez and Hz both are 0, that means we are talking about now the fields which are transverse electric and transverse magnetic field. That means this field distribution must be same as the transverse electromagnetic field. So, what we conclude is a very important and very profound conclusion, that when Ez and Hz both are 0, which represent the transverse electromagnetic wave, for this wave H must be identically 0. So, third case, when Ez and Hz both are 0, we get wave which is TEM wave, transverse electromagnetic, and for this H has to be 0. Now, if you look at this expression here, which is giving me now the phase constant of this particular field distribution, I can take it on this side. So, from this expression I get the quantity beta bar, that is square root of omega square mu epsilon minus H square. That is what we get from here. So, this is the phase constant of the medium, okay, and omega square mu epsilon is the square of the phase constant in that intrinsic medium which is filling this waveguide. So, what we important conclusion which we draw here is that whether we take a transverse electric case or transverse magnetic case, okay, since in this case H cannot be 0, because otherwise the transverse field will go to infinity, they will become infinite if H goes 0. So, when any of these Hz and Ez are not 0, H cannot be 0, that means H is always a finite quantity, or the velocity proportional to related to this, that means the phase velocity will be a function of frequency. Whereas, if I take H is equal to 0, then this quantity beta bar will be omega square root mu epsilon, and then the phase velocity will become independent of frequency. What that means is that a TE mode or TM mode has to be always dispersive, because the velocity will be a function of frequency, whereas the TM mode has to be essentially non-dispersive, because for this now the phase velocity is going to be the velocity in that medium. So, we draw very important conclusions essentially from here, and that is the TE and TM modes are essentially dispersive. That is one. Second conclusion is TEM mode, which corresponds to H is equal to 0, is essentially non-dispersive. That means, whenever we try to excite the field distribution, which will be either transverse electric or transverse magnetic, then we will always have their velocity varying as a function of frequency, whereas when we take a mode, if at all is exist, and if the mode is transverse electromagnetic, then this mode will always travel with a velocity independent of the frequency. Now, the question whether TEM mode will always exist on a given structure, that is the secondary issue. So, it is possible that every structure you may not get the transverse electromagnetic mode propagating, but what we are saying is, if at all the transverse electromagnetic mode exists on the structure, then this mode will be non-dispersive and it will be traveling with a speed which will always be the speed in the unbound medium which is filling that waveguide. So, by doing this general analysis, we reach to this very profound conclusions, and now using this expression which we have derived, now we can analyze a particular waveguide problem. Before we take up the specific problem, however, let us write down these quantities very explicitly, which is del transverse for this component Hz. So, if I have some quantity, scalar quantity psi, which can represent either Hz or Ez, then I can write the del transverse cross some scalar quantity psi times the unit vector, that is equal to x, y, z, d by dx, d by dy, 0, 0, 0 psi. So, we expand it, this quantity essentially would be equal to d psi by dy with unit vector x minus d psi by dx with unit vector y. And similarly, we have this gradient, transverse gradient of some quantity, scalar quantity psi, that will be equal to d psi by dx x plus d psi by dy y. So, once you get these quantities now explicitly written in terms of the derivatives with respect to x and y, then we can calculate these transverse component Ex, Ey, Hx, Hy in terms of the longitudinal components Ez and Sz. So, in Cartesian coordinate, then we can use this expression to get the transverse field component in terms of the longitudinal components, and then the expression essentially would look like that. These expressions are quite symmetric, in the sense, if I look at Ex here, you have minus j omega mu upon h square, dh by dy minus j beta, where beta is the phase constant of the mode, upon h square d Ez by dx. But if I compare these Ex and Hx, essentially minus j omega mu if you replace by epsilon and Hz is replaced by Ez, you get the expression for Hx. And similarly, you can see for Ey also that this is j omega mu upon h square dhz by dx minus j beta upon h square dez by dy. So, again if I replace j omega mu by minus j omega epsilon or j omega epsilon by minus j omega mu, then this expression becomes this. So, interchanging Hz with Ez and replacing minus j omega mu by j omega epsilon, essentially we get the expression for the magnetic fields. So, the expressions are quite symmetric in that sense, and they are very easy to remember also. So, with this now development, general development for the propagation of a mode inside a waveguide, now we are prepared to take up very specific cases, and as we saw that there are two types of mode which can exist, the transverse electric mode and the transverse magnetic mode. We also saw a special case which was the transverse electromagnetic mode, and now we take a very specific case, that is what is called a rectangular waveguide. That is, if the cross section of this pipe which we talked about is rectangular, then what kind of fields are going to propagate inside this waveguide. So, in the next lecture essentially we investigate the propagational characteristics of TE and TM modes inside a rectangular waveguide.